Welcome to our first tutorial on gas law. Here we're going to be looking at the Boyle's charge and the ideal gas equation. Now these two laws are studying the effect on the volume of a gas as the temperature or pressure may vary. So that from the first law, which is the Boyle's law, it makes a simplification with the volume and the pressure, where he stated that the volume of a fixed mass of gas is inversely proportional to the pressure at a given temperature, or provided that the temperature is constant. So what we mean here by inverse proportional, let's put it down. So that V is inversely proportional. Inverse, we put 1 over what it is inverse proportional. It's inverse proportional to P. Now what we are telling here is that because V is inverse proportional to P, if the pressure of a given mass of gas at constant temperature is going to increase, the volume will decrease. And if the pressure decrease, the volume is going to increase. So they are not working hand to hand. That's why we use inversely proportional. And this could only occur when there is a constant temperature for a given mass of gas. All right, so as to going to work further, we are going to remove this to put a constant. Putting a constant, we're going to have that V is equals to, because we remove this, we put K multiplied by 1 over P is going to give us K over P. Now we try to make the constant the sort of the formula so that we know for every given gas we have to make the K sort of formula. Here we can dash 1 over here, use this and multiply by this. We have that K is equals to V multiplied by P. Now we have gotten that for every gas, Vp is going to be constant at a constant temperature. All right, at a constant temperature. Now we have two statements of facts. We assume, for example, let's say this is a pressure and this is a container over here, and we have the volume of the gas to be occupied in this point here. So that this is our pressure, which is called the P1 or the initial pressure, and the volume as V1 or the initial volume. Now assuming at a point in time we are going to increase this pressure, maybe the pressure will now be something of this form, as you can see. Then we have the container over here. We have the container over here, and this is now the gas. This becomes the second pressure value, and this becomes the second volume value. Hence, because the law states that Vp is always constant, as you can see, the pressure was P1 and V1, and you can see that the volume of the gas was much here. But when we increase the pressure to P2, the pressure has been increased, the volume becomes V2, a new volume of the gas, and that volume will be more smaller, or it will be lesser than the first volume. Now what I want to explain here is because the constant said that Vp is going to be constant for every given gas at constant temperature. What is going to happen here, since P1 and V1 is a constant, hence the P1 and V1 I have for this gas here, this container at initial state, is still going to be equals to the P2 and V2 I have for the same mass of gas in the second stage. That is where the pressure has been increased. So that we can now state from here that P1 V1 is equals to P2 V2. That is, we consider initial pressure of a gas, initial volume of a gas, now was suspended to a new pressure and a new volume. Since the constant Vp for every gas is like that, that means the P1 V1 is going to be equal to the P2 and V2. So here is our gas law equation for Boyle's law. All right, now we move over to the charge law. Remember, we talk about what we have here as the volume and the pressure with constant temperature. So the temperature will not change for this to occur. Now the charge law studied the volume and the temperature, how the volume is going to change with a change in temperature. And he makes a note that the volume of a fixed mass of gas is directly proportional to the temperature at a given constant in pressure, or if the pressure is constant, or provided that the pressure is constant. So that here we can state it as the volume is directly proportional. We use a direct method which is directly proportional to the temperature. It's not inverse. If it's inverse, equal to 1 over T, but it is direct, we leave it like this. And what does it mean? It means that if the pressure goes high at a sunny day or at an increase in temperature, the volume of that gas in the container is also going to increase. But if the temperature is going to decrease, the volume is also going to decrease, because they are working hand to hand. That's what we mean by directly proportional. So the volume of a given mass of gas is directly proportional to the temperature, provided that the pressure remains constant. So here we're going to bracket it here and put P at the side of it, meaning that P is constant and for a given mass of gas. Now, just like we do here, we need to find the constant of proportionality, so that we're going to have that V, removing this, we are going to put equal sign, putting the constant. The constant is going to multiply by T to give us KT. We try to find the value of K. We know that we're going to divide both sides by T, divide by T, so that this can cancel, and we have K equals V over T. Now, this is constant. The constant is V over T. The volume over temperature is going to be constant for every fixed mass of gas at a constant pressure. V over P is always the same. Alright, now what do we note here? We also consider a volume of a gas at V1 and a volume of V1 and temperature at T1. Suppose that the temperature was increased, that means we now have a new value of the temperature represented as represented as T2. It is going to cause a change in the volume, which we are going to take the value as V2. Now, because V over T is constant, hence in that same gas or mass of gas, we are now going to find out that the V1 over the T1 will be equals to the V2 over the T2. And this is our equation for Charles law. Now, one of the things here again is that sometimes we do have to find the ratio of the volume and the temperature in Charles law question. If you want to do that, this formula could be written as V1 over V2 equals T1 over T2, whereby the ratio will now become V1 ratio V1 ratio V2 is equals to T1 ratio T2. I want to look at a question on that as we go on. Now we move over to the ideal gas equation. This ideal gas equation now combines the fact that most times the temperature and the pressure might not be constant, because for here we assume that the temperature must be constant, and in this case we have that the pressure must be constant. Now the ideal gas equation is talking when the temperature and pressure is not constant. So we're not going to have the Charles law governing it. We're not going to have, the Charles law governing it and the Boyle's law governing the gas law of that particular gas. So what do we need to do? We need to combine these two statements of fact on the same volume, so that the ideal gas equation is an equation gotten by the combination of the Boyle's law and the Charles law. Now, from this particular place here, we have that from this particular place here, I want to work on the ideal gas equation. So we have that the ideal gas equation is a combination of the Boyle's and the Charles law. We are going to have that V is going to be directly proportional. Let's start from here. Directly proportional to T, and the volume also is going to be inversely proportional to the P. So for ideal gas, we are combining the both statement of fact from Charles law and gas law to form the ideal gas equation for a gas whereby the temperature and pressure is not constant. So now I'm going to remove this proportionality sign and introduce an equal sign and just a one constant, so that V is now going to be equals to one constant multiplied by 2 multiplied by 1 is still going to be the same thing over P. All right, we still want to know the value of the constant, so that if K is to be made set of formula, we are going to have that V is equals KT over P, whereby we cross and multiply. If you cross and multiply, you find out that P is going to multiply by V, all right? But want this to come over to this side, making K sort of formula, we are going to have that K T multiplied by here and V multiplied by P is going to give us VP, all right? Now, again, we divide by the coefficient, which is T, and we divide by T. We are looking for K. Divide, cancel this here. We want to have that K is equals to VP over T. Or in more general way, we have it to be equals to PV over T. Now, since this here is a constant, that is K, it means that for every mass or for every gas, PV over T is going to be constant. All right, that is if the temperature and pressure does not vary. Hence, we are now going to consider for the statement of fact whereby we have the initial volume of a gas to be V1 and again the initial pressure to be P2. Now, we also have the initial temperature to be T1. Now, assuming there was a change in the temperature to T2, and there was also a change in the pressure, sorry, which is P1 to P2, and there was also a change in the volume. Now the change in the volume will now be resulted from the change in the temperature and the pressure. To be able to get the change in the volume, which I will represent at S as Vs, we are going to have that since PV over T is constant, hence for this first state of the gas, which was in P1 and V1 all over T1, it is still going to be the same on that new state of the gas, which the volume, which the pressure and the temperature was either increased or reduced. So that we're going to have this is going to be equals to the P2 multiplied by the V2 over the T2. All right, so this here, what we have here is what we call the ideal gas equation. Now, again, for instance, we can use this equation to solve any problem in gas law. For instance, now, let's assume that the temperature was constant. So the temperature from T1 to T2 is the same thing. So it is constant. It does not change. Hence, T1 is going to be equals to T2. We are now going to have this expression to look like this. P1 V1 equals to P2 V2. This is the new expression we're going to have because the temperature is constant. That is taking us back to Boyle's law, which is what we have here. And also, we are going to consider maybe, for example, the pressure is also constant. So the pressure in P1 and P2 are the same thing. It does not change. There's no change in pressure. So it is constant. This expression will look something of this form. V1 over T1 equals V2 over T2. And this we have here is going to take us back to the Charles law equation, which is here. Charles law equation, that is for constant pressure. Now that is all for this video. Hope you learned something. In our next video, we want to look at question on this, and also we're going to look at more gas law such as the Avogadro gas constant and as well as the volume or partial